Swayam Prabha. Digital India. Educated India.
So what we are here is to talk about dispersed multiphase flows. Okay, so I want to start with sort of parsing this dispersed multiphase flow. Dispersed in the sense that we're talking about fluid containing particles, droplets, and bubbles. Okay, so you will have a continuous phase like this blue colored fluid here. That's the continuous phase, and within it you have dispersed phase, which are solid particles, droplets, or bubbles. Okay, there are other kinds of multiphase flow where you have waves on an ocean. There is a air-water interface. That's a multiphase flow. Slightly different kinds of tools are needed there, so I'm not going to focus on that. So mostly what I will talk about is problems that are related to particles and droplets and bubbles. Now, as all of us know, is each of those phases, both the continuous phase as well as dispersed phase, can be gas, liquid, or solid. And also there's no reason for limiting to 2 phases. You could have 3 phases, 4 phases. And of course, the more difficult the problem gets. Okay. You can have 9 different combinations because continuous phase can be gas, liquid, or solid, and dispersed phase can be gas, liquid, or solid. So there are many examples. So you can have what are called gas solid flows, and I've given a bunch of examples: volcanic eruption, dust pollution, so on. And gas liquid flows, you have rain or fuel spray, or even when I'm talking, I'm throwing a lot of droplets around. So those are gas liquid flows. Gas flows doesn't make any sense because one of the things that brings to light is that they are not going to mix easily. When you have a multi-phase flow, if everything mixes very quickly, then there's not that becomes a single phase. Okay, so therefore gas is out of question. And of course you can have liquid solid, liquid, and liquid gas. So very many different. So in one stroke we are trying to, in this course, cover some basics that will apply to all these problems. Okay. Of course, can the continuous phase be solid? Can you have a solid flow, solid liquid, or solid gas flows? What do you guys think?
I think so. Yes. Powder is flowing and there is a lump of solid in it. So the powder behaves like one fluid and the particle behaves in the other phase.
That's right, but I'm talking about the continuous phase being solid.
Powder.
Yeah, you're right. You could have a powder and
in which it's flowing through a slope.
Yeah.
A lot of powder sand flowing through a slope, and there is a lump of solid
inside it. No, you're absolutely right. I was also thinking of, for example, in high-speed flow shock problems, this is a very important thing because you can have a solid within which you could have voids. It could be an explosive, for example, and you smack it very hard, it starts flowing. So in other words, what becomes a solid at a very high strain rate may behave like a fluid. It may not behave like air or water, but it may end up flowing. So you could have very complex sort of dispersed multiphase flows, and as he points out, you could have a solid powder flow in which other particles could be embedded in there. Okay, so every variety is there in this problem. And also one of the things that makes really vexing is that too many terminologies. There's particle laden flows, droplet laden flows, liquid sprays, bubbly flows. So one of the things is then there is no one set of governing equations. It's not like Navier-Stokes equation. That's one set of equations there. You go there and you solve it, then you're done. Multiphase flow, what makes it very hard is that there are no one set of go-to equations. Everybody decides upon a certain set of equations, and usually very smart people, therefore they make a lot of assumptions depending on their application. And this whole course I'm going to talk about is that how do you simplify the governing equations so that you can get something useful out of your analysis. Okay, so that's the kind of focus. So be careful that there is a lot of interesting physics there, but there is also a lot of confusing terminologies out there. Now, one of the things I would say is that if somebody asks me what problem you're working on, I say that it's sort of every problem around us, virtually in some ways or other, it's a dispersed multiphase flow. So you have from volcanic eruption, so a lot of problems in nature are multiphase flow. So you have a dust storm, here supernova, or it could go to the other extreme. These are all these other three problems are very gigantic scales. Okay. On the other hand, you have red blood cells flowing in or a engineering problem such as a fuel spray or cleaning of wastewater. Okay, so there's examples are galore. Okay, what makes multiphase flow really interesting and at the same time really hard is the fact that you have two phases and they are talking to each other. Okay, so you have the fluid phase, the liquid or the continuous phase, many different ways I will call that. Okay, so it's sort of like this is the one that permeates everywhere with holes in it. Okay, and the dispersed phase, which are sort of in this case I call them particles. By the way, I will call them particles, but it could be droplets or bubbles as well. Okay, so you have two different phases, and we all know that fluid partials to talk to each other. In other words, they rub against each other. So you have a fluid set of Navier-Stokes equation. So that's what takes care of fluid interacting, sort of the continuous phase interacting with itself. Okay, and the continuous phase interacts with the suspended particles, droplets or bubbles. Okay, so by applying drag force or lift force, heat transfer, or it could have evaporation, mass transfer. So the continuous phase talks to the dispersed phase, and the dispersed phase will talk back to the continuous phase. Forces applied on the particles and droplets by Newton's third law must be applied back. If there is evaporation, it must go to the continuous phase. So there is what is called a two-way coupling. Continuous phase talks to the dispersed phase and dispersed phase talks to the continuous phase. Just like the fluid is interacting with itself and described by the Navier-Stokes equation, the particles can interact with themselves. They can collide. That's the easiest interactions. And also one of the interesting thing is that, and we will talk a lot about this, which makes modeling very hard, is that the particles talk to each other as mediated by the surrounding fluid, sort of bicyclists going behind each other. Okay, so one riding on the wake of the other. Okay, so those kind of interactions are between particles but at a distance. In other words, they are not touching each other. So particle-particle interaction at a distance is one of the biggest challenges in multiphase flow, as we will see. So any problem that you have in dispersed multiphase flow, whether you have fluidized bed or whether you have blood flow, and you want to describe that mathematically or you want to do the simulations, it's a pretty complicated problem. It's not going to be simply Navier-Stokes equation. You got to take into account how particles are interacting with each other through collisions, through indirect interaction, and how the fluid applies forces and heat transfer on the particles, and how the particles feed that back to the fluid. All of them have to. So in other words, much of this course is in this particular picture. How do we translate this understanding into a set of governing equations? And as I mentioned, there is no one set of equations that will capture this whole physics. Sometimes you might say, well, the back effect on the fluid is not that important because there are too few a number of particles there, so let's ignore that. Or you may say it's very dilute. Why bother with interaction between particles? That's the kind of judgment we will learn to make. When to throw things and when not to throw. You want to throw the bath water but not the baby with it. So that's the separation we will learn to make in this course.
Sir?
Yes.
Can you move back to slide?
Yeah.
So in this diagram, we are considering particles as dispersed medium.
Yeah.
We'll consider fluid as a fluid field or a fluid particles we'll consider.
Yeah. So you're asking about modeling questions. We are going to cover that. But when you think about it, what you have is a continuum, which is the fluid phase. And it exists only outside the particles. And the particles, if they, mostly we will talk about rigid particles, so they follow rigid body dynamics. So you don't have to worry about the flow inside. But if you have a droplet or a bubble, flow inside can also be important. So you have to consider all of them. So there is interaction happening between the outside fluid and the particles. So when I talk about the fluid is interacting with the particles, I am talking about truth, which is you have to look at the pressure field around the particle, shear stress around the particle, each and every particle, and you want to see how they move. Okay. In fact, yours is a great question. So that's what makes this problem really hard, is that let's say you have a fluidized bed. There are a trillion particles in there. Literally speaking, you got to take each of those trillion particles, look at the fluid mechanics around it. Even if they are rigid, they are moving, rotating. You got to take care of all those things. When I draw this picture, I'm talking about everything, like playing God. We know everything, okay? But then obviously that's not possible with a finite computer. So how do you make those judgments? How do you make those reductions? How do you make it simple? So it's a question of modeling. So as the saying goes, all models are wrong. Some are useful. That means we understand the full physics, but then we try to reduce it to something that's solvable. You get useful equation. If it is just an algebraic equation, so be it. Or if it's got to be a supercomputer simulation, we got to do it. Sometimes the problem is so hard that we will get only approximate answers. So those are the kind of stuff. So at this stage, I'm talking about the whole story. Okay, I haven't started making any assumptions yet. Any other questions? So one of the things that makes this problem hard, as you asked, is that the range of scales is too many. Okay, when you go to very small scales, you may have issues such as viscosity, thermal conductivity, and so on and so forth. So those are, we are not going to talk about this a whole lot. So we are going to take them for granted that we know the viscosity of the fluid, and the particles say are rigid, and so on and so forth. But now you also have microscale physics in the sense that you have particles, they may be 100 microns, millimeter, depending on your application. And you can also think in terms of interparticle distances. Maybe on average they are a millimeter apart, and so on. So you could look at it from a microscale point of view, what's happening around one particle, what's happening around a cluster of say few hundred particles. Okay, because if they are going to be influencing each other, you need to know how they line up. Do they all line up one after another, or are they completely random? Those kind of questions become important. Now another thing that's very interesting, what happens is that these flows naturally segregate themselves into clusters of particles. Okay, and I will show some examples of it. Say this is one video, you may have seen this. This is a fluidized bed, circulating fluidized bed. It was taken at NETL. Okay, it's a really beautiful video. Let's see if it plays. Okay. So you can see they will keep zooming in. So now it's zoomed in. You can see clusters of particles and void regions, so you can clearly see that. So I would call this a microscale view. What's happening around individual particles and their interaction. Okay. Now when you zoom out, you will see mesoscale. Mesoscale are the big sort of clusters of particles and void that you see. And the macro scale could be your entire setup. So in other words, one of the nice thing about multiphase flow, dispersed multiphase flow I see is it naturally lends itself to this division. So what happens is that we cannot take care of every single particle and what goes on around each of them and at the system scale at the same time. So our best strategy is divide and conquer. And divide and conquer, in this case, many times if you just have a turbulence, the same problem occurs even in a single phase turbulence. But one of the biggest challenge there is, how do you divide? What do you divide? So here, nice thing about multiphase flow that I find is that there is a natural length scale that tell you, okay, you know, I can look at 100 particles or 1,000 particles, that's your micro scale. Maybe I look at maybe 1 million or 2 million particles, they form like layers of particles of clusters. Maybe I can study them. Then we study the whole system, okay. So in other words, this multi-scale nature of this problem is something that we are going to be focusing on. So if you want to study a fluidized bed in its entirety, of course you can go and throw it in the computer and there will be lots of models in there and you produce pretty pictures, etc. But what I want to talk about in this course is that you want to be questioning all those models that go in. So if you simulate the whole fluidized bed, is your simulation understanding the fact that there are layers of clusters and voids in there? How do you take care of it? Or are you worrying about the drag forces on individual particles? Have you taken it correctly? Particle-particle interactions being taken into correctly? They are all there in the models, but how good the models are. Sometimes they are good and you may say, yes, it's fine. Sometimes you may say, well, this model is good, but this model is not good. The uncertainty in this or error in this model is very big. So I want to improve that. For that, then you may have to go to a micro scale or a meso scale study that smaller scale in more great detail, develop your models and then send them to your big simulation. How do you do those things? Those are the kind of stuff I would like to discuss in this course towards the end, okay. Now in terms of introduction, what really what makes this problem multiphase flow really hard is they're invariably turbulent. It could be classical turbulent or it could be what are called pseudo turbulence. Even if you have a low, slow moving laminar like flow, since particles are always going to be randomly distributed, they are going to bump into each other randomly. Even in a laminar flow there is going to be what is called pseudo turbulence. So this random position and motion and the chaotic flow around them makes this, contributes to what are called pseudo turbulence. So the particles, in some ways you can argue that, hey, they are going to be increasing the turbulence. So they are going to change the turbulence of the flow. So if you have turbulent closure models, the fact that you can't simply use the same closures that you use for a single phase flow. You have to use multi-phase closures. For that you need to know how particles change turbulence. But you can also argue that particles and the fluid are rubbing against each other, so there is a lot of dissipation. So does turbulence increase or decrease due to presence of particles? I don't think there is a very well understood answer or simple answer. It depends on problem. And also what may happen is small scale turbulence may be damped and medium scale turbulence could be enhanced. So the answer is nothing but simple. So this multi-phase turbulence is a very important thing that that makes problem really hard. So in essence, multi-phase flow turbulence is not the same that you would exist if you removed all the particles. Say for example, if you have a pipe flow, people know for a single phase gas phase or liquid pipe flow turbulence, there's a lot of literature, there's a lot of understanding, a lot of models. But if you throw in there a lot of particles in there or bubbles in there, you just can't use the same turbulence models anymore. It just changes and the problem gets really hard. In fact, we know what the pipe flow, turbulent pipe flow profile. Now depending upon the size of the particles, density ratios, the turbulent profile can profoundly change. Therefore, and people don't know offhand what the answers are, and that's what makes multi-phase flow very rich problem. Okay.
So Bala,
Yes.
So if you have a laminar flow and you were to put particles in, could it become turbulent?
Yes, that's also. So in other words, it is what I call it, if you go put a probe, velocity probe, in a laminar pipe flow and you put particles, you will see signatures. It won't be a single phase. In a single phase, at that low Reynolds number, you may get a constant velocity measured by the probe. But what I am talking about is each time the particle goes, you could have a wake effect of the particles and you have signatures, and the particles are arriving randomly because they are not in a lattice there. Therefore, you will get turbulence like signature. In fact, your question is very good that some of the Kolmogorov theories don't apply necessarily to this turbulence anymore. So the closures that people use for single phase turbulence is not necessarily good for multi-phase turbulence. And I will say more about that. The other thing also is in turbulence, when we say turbulence mixes, right? So when you put particles, let's say you have a bucket, that's the usual example I use. You have a bucket, you stir, you create turbulence, and you put a lot of sand in it. Very, let's say not worry about settling, okay? The question I ask is, will the sediment concentration going to be uniform? You would think so, right? You drop a ink in there, some dye, it will spread very well. What turbulence does is it mixes. So, so you would expect that the turbulence will mix particles very well. But the strangest thing is that turbulence also demixes particles. Easiest way to think of it, that turbulence is a bunch of eddies moving around. What do eddies do? It spins out particles, heavy particles, and things that are light, which are like bubbles, go to the center of the vortex core. So when you put particles, naturally they will demix. So there is mixing as well as demixing. So turbulence plays dual role. Just like particles, how did it affect in the previous slide? I said it can enhance turbulence or damp turbulence. And turbulence can mix particles or demix particles. So the point is that it's a very complicated problem. Yes?
I think so cohesion and adhesion might be responsible for this thing, the change in mixing and demixing of the bubbles and all. Is there any other parameter or any other thing responsible for this thing?
Collision will play a role, but think of it this way. You have a eddy spinning around and you put a particle which is heavier than the particle, it will go, but it will not follow the close to streamlines of the fluid because the particle is heavier. It's sort of like you having a stone tied at the end of the thing, and you do this, you let go, it wants to spin out. Same thing happens, heavier ones will spin out. So particles in a vortex will avoid the core of the vortex and they will congregate at the outside. That's called preferential accumulation. Whereas on the other hand, lighter things like plastics, bubbles will attract and come to the center of the vortex. And this is really happening because in the ocean there are big gyres and all the garbage that we throw in gets collected at the center of the vortex core. So this is a general rule. Lighter particles go to the center of vortices and heavier particles get spun out. Therefore, in turbulence, if you have particles, if they are very small, they behave like molecules, they will be evenly spread. But when they get to the right size, they may get spun out depending on the density ratio, or they could aggregate in some specific regions. Therefore, if you got a turbulent flow and you want to know where the sediments or sand particles are, well, it depends. Okay, if the Stokes number, which I will talk about later, is the right, they will demix. They will not be uniformly distributed. There will be regions where there are going to be more particles. There will be regions where there are less particles. Okay, so that's what I was talking about. Yes.
So do you expect the behavior of the particles at a micro scale to mimic the behavior of the atoms at an atomic scale when we're looking at that?
It will not, because atomic scale processes are generally non-dissipative. Okay, but molecular scale processes are dissipative, and so there is no analog, for example, for demixing in a molecular scale. Okay, so there are, that's what it's actually a great question. We try, or at least in my group, I try to get a lot of inspiration from molecular dynamics and those atomistic scale processes in modeling, but those interactions, or those lessons that you learn, can only go so far. The analogy is not perfect. Okay, so nonlinearity and other things will make that's what makes fluid mechanics much harder in a way. Okay, because the molecular processes you could average and you call pressure, viscosity, thermal conductivity, things that nicely come out, but there is no universal closure model for turbulence. And now particles behave the same way as fluids, so closure models of multiphase flow is not universal. So that's bad, but on the other hand, that gives us all the job. Okay, so because the problem is not solved. Yes.
So does that mean it's kind of a scale problem? Like the problem that's coming in my head is like if we are looking under a microscope at a small vein, then we would consider like red blood cells to be separate. But if we're looking at like a lot of blood flow, we would consider it as a continuous medium. So like, can we make use of that?
That's what I was talking about, is that in most systems you could look at it, what's happening at the particle scale, at the micro scale, how they interact and so on and so forth, and you might get some inspiration from atomic scale processes, how they interact. But then you see those that look at this problem, look at these flows. I mean, they don't look pretty at all. I mean, you look at this problem, there are so many different scales, and so one needs to sort of look at this problem at the micro scale, at the meso scale. You can see cauliflower like instabilities happening. So if I ask you how a volcanic eruption spreads, okay, because this is an important problem for air traffic and so on and so forth, how do you solve this kind of problem? I mean, it goes on kilometer scale, and that's the kind of knowledge that we want to try to attack here. The other thing is that what I wanted to talk about is that these flows don't behave like laminar flows. I mean, like there are instabilities. They do not organize themselves into particles, don't uniformly spread everywhere, because that would be very nice. Okay, see, in atomic scale processes you have randomness, and randomness, if it is sort of predictable way, you can average easily. Here, when there are lumps here and there and you don't know how they are distributing, even averaging becomes hard. So that may be your answer to your previous question, is that what makes the problem hard is that we all know that, okay, we need to average, but when you're averaging over a certain volume and it's not uniformly painted there, how do you average? It changes from problem to problem, and that's what, therefore you need to understand, when you're averaging over a meter scale, you want to know what's happening on 10 centimeter scale, 1 centimeter scale, on 100 micron scale, and the processes are very complex. So that you really have to come to grip with what's happening at every scale if you want to have good models at the macro scale. And that's what we lack, and hopefully we will all contribute to those model development and closures. Okay, and you can see in this problem, okay, look at these fingers forming. Okay, it's not like, so initially it was so this is a sector of a cylinder, so the particles were in nice annular region and they were hit hard, and when they are not going as a uniform front, they somehow form fingers. And some want to go first, others don't want to go, and you need to know how that's happening if you want to describe this mixing phenomenon, at least in this case. So what I going to do is that I have broken up the topic into many sub lectures. Okay, some of them longer, some of them short, and then we will stop, and then I will take questions, and then we will go start another one. Okay, yeah. Any questions on that so far?